Hi everyone, welcome to the Climate Confident podcast. My name is Tom Raftery, and with me on the show today I have my special guest Arnaud. Arnaud, welcome to the podcast. Would you like to introduce yourself?
Hi, my name is Arnaud Lager. I am the CEO and founder of Decahydron. We are a startup specializing in carbon-negative hydrogen in Ras Al Khaimah in the UAE.
Okay, so I'm guessing the majority of people listening to this, Arnaud, have never heard of carbon negative hydrogen. Can you explain that concept for us, please?
Yes, it's a concept we came up about 2 years ago when we were looking at all the different ways of making hydrogen. And we've noticed that at best, to make hydrogen, you are carbon neutral, and that is really at best. What we noticed is that a lot of people are talking about hydrogen and CO2 sequestration, but nobody really thought about putting the two together. And our objective is to create hydrogen by cracking methane, which is called blue hydrogen, but also to link it with the local cement industry that we have here, that is emitting about 3 to 5 million tons of CO2 per year. So our objective is to create our hydrogen and use our facilities to capture the CO2 from their cement plant and turning them green. At the same time, we are lucky enough here in the UAE to have some very special rocks, which are called ultramafic, where we can inject the CO2 directly, and it will turn the CO2 into a carbonate minerals. So we'll turn it back into stone. And that would sequester the CO2 permanently without any chance of it leaking back to the atmosphere. That is our plan.
Okay, so a two-pronged plan: generate the hydrogen, capture the CO2, and then put the CO2 either into concrete with local concrete manufacturers, or inject it underground in rock formations where it will be permanently sequestered. Is that a good summation?
It is a good summation, and the vast majority, in fact, is going to be injected underground in this ultramafic rock and turned into a carbonate minerals. Some of the CO2 can be turned back, as you said, into the cement plant to be reintroduced in the cement. But the vast majority is going to be sequestrated underground.
Okay, and talk to me a little bit about this rock, because it has some unique characteristics that make it particularly suitable for this, right?
Yes, it is quite unique. It is, in fact, the crust and the mantle of the Earth. And normally it is situated 20 kilometers deep underground. But here in the Al Ajjar mountain in the UAE and in Oman, it has been thrusted up to the surface. And it is quite unique in the UAE. And there's there's cubic kilometers and cubic kilometers of this rock. I mean, it is about 60 kilometers wide, 700 kilometers long, and 10 to 20 kilometers deep. And it's very reactive with CO2.
Wow.
If you inject CO2 into it, in a couple of years, all your CO2 will be turned into a rock. And there's enough of this ultramafic rock to be able to sequester all the CO2 that we are emitting currently and in the near future. So it's a very, very important tool to fight global warming.
Okay. Give me a little bit of an idea of the scale of the amount of CO2 that this rock formation could sequester.
Well, it could sequester about, I would say, 200 gigatons of CO2, which would be about a quarter of all the CO2 that we have released in the atmosphere since the Industrial Revolution in the 19th century. So there is a substantial target there. But at the moment, we are just aiming to sequester 3 million tons of CO2 per year. And then if we are successful in this small-scale pilot, we can then look at importing CO2 from other countries, mainly by a boat, and inject it in our rocks. One of the reasons why we want to do it by boat is the UAE and Qatar, for example, are using a lot of LNG tankers that ship the methane to Japan, Europe, or the US. And when they come back empty. And what we want to do is, instead of coming back empty, we fill them up with CO2. They arrive here at port, we unload them, put methane back, or even better, if we could fill them up with hydrogen. And like this, we could clean up the full energy stream of hydrocarbon.
Okay. And how can we tell that the CO2 injected into the rock is fully sequestered, that we don't have any escape? Is it 100% sequestered? Is it 90% sequestered? And how do we measure and validate that?
So on a geological timescale, it's 100% of the CO2. It will take about, from the test we've done, from 3 to 10 years for 95% of the CO2 to be fully sequestered. And the way we would measure it is, because we cannot have a look underground ourselves, because we will be injecting the CO2 down to a 3 kilometers depth. We will use what is called magnetotelluric method, which we will record the change in the magnetic field of the Earth. Because one thing that happened when we inject the CO2 in this rock, there's a chemical reaction, and a little bit of a mineral called magnetite is being formed. And this mineral has a magnetic property, and we can measure precisely the change in the magnetic field of the area where we're injecting the CO2, and that would tell us how much CO2 we've sequestered. On top of that, there's other geochemical methods that we can use, and also surface monitoring to make sure that no CO2 is escaping. But we know that because we're injecting the CO2 so deep underground, there's very, very little chance that the CO2 will escape. In fact, there's none.
Okay, so you're injecting it, you said 3 kilometers underground. Is it just you're pumping gas down, or are you pumping it down in a kind of a carbonate liquid form?
So there's 2 different ways of doing it. People have done it by mixing it with water and injecting this carbonated water underground. This is what is being done at the moment in Iceland. The issue with this is you need 25 tons of water per ton of CO2. And because we're in a desert here, that's not a sustainable way of doing it. So what we will do instead is injecting the CO2 in a supercritical form, which means that it's neither a gas, neither a liquid. It has property of both. It just means that the pressure is higher, and we inject it at the temperature above 32 degrees centigrade. And by injecting this pure CO2, we avoid injecting water, and it is the water that is already present in the ground that is doing the work for us, and will slowly turn the CO2 into carbonate minerals.
Okay. And 3 kilometers seems a long way down. Is that standard, or is the reason for this something to do with the local geology?
So there's 2 reasons. First is the deeper we are, the safer it is, and the best it is that we are sure that the CO2 will not rise up to the surface. And also 3 kilometers is down to the geology, where we know at this depth that we will encounter the right rocks that will have the right permeability so that we can inject our CO2. 3 kilometers sounds deep, but the local oil field here in the region are down to between 3 to 6 kilometers. So it is fairly standard in the oil industry to drill at those depths.
Okay, interesting. And so that's the carbon capture side of it. Then there is, you will be splitting methane, cracking methane to create hydrogen. What are you hoping to do with the hydrogen?
So our first client that we are aiming for is linked to the cement industry. It is for the local quarry, which use a lot of very big mining trucks. There are 100-ton mining trucks that are running diesel at the moment. And in total, those trucks are emitting 1.5 million tons of CO2 per year, which represents 0.5% of the CO2 emission of the UAE, which is quite a lot for just about 200 trucks. So our aim is to get those trucks with hydrogen so that we can remove the diesel from them and prevent 1.5 million tons of CO2 being emitted. At the same time, this hydrogen will be cheaper for them to run than diesel, because the hydrogen that we will be producing comes from blue hydrogen, so from methane, and it's a lot cheaper than having hydrogen from green energy, like electrolysis. Our cost will be below $5 per kilo, whereas at the moment in the UAE, green hydrogen is above $10 a kilo. And the break-even cost with diesel is about $5 to $6 per kilo. So that is our aim.
Okay. And longer term, you mentioned potentially exporting hydrogen. Where would that be to, and for whom?
The UAE has issued a hydrogen roadmap where they want to produce 50,000 tons of hydrogen per day for the local and international market. How this hydrogen is going to be transported, we are not 100% sure at the moment. Is it going to be in hydrogen form or under the form of ammonia? Ammonia seems to be most likely at the moment, even if for me as a chemist, working with ammonia is not the most pleasant thing to do. It is very problematic, especially personally, I wouldn't put it on a boat to transport it, because if people think that an oil tanker having a spill on the beach is bad, ammonia is going to be way, way worse. But that's a different subject. Our aim for the hydrogen is at the end to replace all the methane. And my dream is for the UAE to not export methane anymore, but export hydrogen. And we remove all the carbon from the methane here locally, inject it in the ultramafic rock, and export the hydrogen. And I think that is one of the way of fighting climate change.
Interesting. There's another topic that we should really talk about as well, and that is that there are deposits apparently of hydrogen naturally in the rocks in your region. Can you talk to me a little bit about that?
Yes. So those rocks, the ultramafic rock, also, when they react with water, they produce hydrogen. And we know that in Oman and in the UAE, there's about 150 different locations where you can see hydrogen bubbling up. One of our projects is to look also for this natural hydrogen. It has never been done in the UAE before. We are going to be the first one to do this with our partner, Rag Gas, here in Ras Al Khaimah. And we hope that the reserve of natural hydrogen in this area is as big, if not bigger, than all the methane that was already discovered in the UAE. Potentially, it is completely a game changer for the energy stream, because the production cost of this hydrogen, from what we calculated, is below $1 per kilo. So that would be 10 times cheaper than what green hydrogen can do.
Okay. And of course, there is no CO2 associated, or minimal CO2 associated with the extraction of hydrogen, which is just underground. Are there other places in the world where there are hydrogen to be tapped and extracted and used as well, or is this another unique aspect of your local geology?
No, there is plenty of places around the world where hydrogen is present. It's quite a bit of an embarrassment for the oil and gas industry because we know about it, we know where it is, but we never really looked for it or even thought of producing it. I mean, the only natural hydrogen reservoir that is producing at the moment is in Mali. And the legend behind this reservoir is that an oil company drilled a well, an exploration well, to find methane. And they never found methane.
Uh-huh.
And because the tools we use to monitor the fluids on the ground, we are looking for carbon and hydrogen, but never just for hydrogen. Because if we look just for hydrogen, only the water will show up. So we only look for the two signal, carbon and hydrogen. And they saw the hydrogen, didn't see the carbon. So they thought, well, it's water, let's shut the well. And what they did, it's instead of shutting the well, they turned this well into a water well for the local village. And the local village had a water well, everything was fine. And the legend goes that one evening, a shepherd decided to go and have a smoke next to this water well and threw his cigarettes down the well. And the well caught fire, and that's how we discovered the hydrogen. I'm not sure it's 100% true, but it's a nice story. And since then, the well has been producing some hydrogen, and the local village use the hydrogen to produce electricity. So it is a very nice story, and it shows that natural hydrogen exists and it can be exploited commercially. There is some places in France where I'm from where they have reported some hydrogen reservoir in coal seam. There is in Spain also. But if you look at the literature, there's plenty of other places in Russia, in Canada, in the US. Everywhere where we're going to start to look seriously, I think we are going to start finding hydrogen.
Wow. And are there any particular difficulties extracting it as opposed to extracting methane, for example? You know, it's a different molecule, so is it more challenging to extract, or does it make a difference?
At the surface, it won't be much more challenging because we've been producing hydrogen in oil refinery for a century now. So we know how to handle it in pipes, and we know how to store it, even if to store it at such a big volume is going to be a challenge, but it's not a very difficult challenge. On the subsurface side, however, we need to rewrite the rule books on how we can predict how much hydrogen we can produce from our wells, and this is going to take some time. Basically, it's like going back to the oil and gas industry 100 years ago. So hopefully it's not going to take us 20 years to learn everything. We can do it a lot more quickly now that we've got computers and the knowledge from the oil industry, but there's still some challenge.
Okay. And where are you in terms of the production cycle, I guess? So you're just at the very early stages of figuring out how to sequester the CO2 right now. Is that it? And you're going to take from there. So talk me through that process of going from where you are today to where you want to be in 2, 3, 4, 5 years' time.
So our plan is first we need to finish the exploration phase. So we've already done some exploration where we looked at what is called gravimetric survey, where we flew a plane over the mountains to look at magnetic and gravimetric anomalies, which could tell us where a reservoir could be. So we've done that. We will do some more tests, and then we will start drilling an exploration well, where we will drill down to first 1.5 kilometers, take some rock samples and see what the rocks looks like, because it's the type of rocks that the oil industry never really looked into it, because we know normally there is no methane, there's no oil in this type of rock. So we never really looked at it. Okay. So we will drill our exploration well, see if we can find some hydrogen in a shallow reservoir, so around 1.5 kilometers, and then we will expand it to 3 kilometers depth. And then we will see if we can see the hydrogen. If we cannot find hydrogen, then this well, we will not abandon it. We will turn it into our CO2 injector. So that is our first plan. If there is no natural hydrogen, then we start building our hydrogen plant and CO2 capture in Ras Al Khaimah. And then we will pipe the CO2 that we've captured into this well. So it is going to be a very, very busy couple of years for us, because that is a lot of work to do.
Okay. And long term, where do you see the company going in terms of A, carbon capture, and B, hydrogen production?
So it will all depend on how successful we are with the natural hydrogen. If we are very successful in the natural hydrogen, then we will need to do what is called appraisal and develop this hydrogen field, which would take, if we follow what the oil industry standards are, would take about 5 to 10 years after discovery. That's also a lot of work. And if we do not find natural hydrogen, then we drill a couple of CO2 injectors, capture the CO2 from the local industry, monitor that it is being sequestrated properly. And once we know for sure that our plan works perfectly, we can start importing CO2 from other Emirates in the UAE and then from abroad. So that is our first phase. Once this is established, we can then start moving to other countries. There is Oman, for example, so just across the border here, where we could reproduce the same business model, and then move to other countries where this type of rock is available. Unfortunately, there's not that many, and they are not as easily accessible than here in the UAE. But with the knowledge we would gain here in the UAE and in Oman, I'm sure we can expand to other countries.
Okay, and what do you think in terms of ultimate tons, millions tons, gigatons, whatever of CO2? What's your long-term aim in terms of CO2 sequestration?
Well, I'm hoping that we can sequester everything that we can find, everything that we can capture. So I'm talking about gigatons and gigatons of CO2 per year, because that is what we need to do. If we do not sequester 40 billion tons of CO2 per year, we are going to end up in a lot of trouble. To give you an example, since 1960s, we have been producing 800 gigatons of CO2 and released it in the atmosphere. And every year we are producing 40 billion tons a year. And that is growing nearly exponentially. So my aim is to first curb this 40 billion tons per year that we are emitting, and then go further, go after those 800 billion tons of CO2 that is in the atmosphere. And the CO2 sequestration techniques capture that we are going to use, we are going to go with a cryogenic technique. And our aim is not only to capture the CO2 from cement plants, steel plants, but also at the same time reduce the level of CO2 from the flue gas below the 400 ppm, which is the level where CO2 is at, so that the air that we release in the atmosphere is not only free of the CO2 that we've added from cement or from steel manufacturing, but also removing some of the CO2 that is already present before we add more. So that is our plan. Our first milestone is 3 million tons per year. And then we hope that in 10 years' time, we will reach the gigaton per year and then grow from there.
Nice. And you mentioned that 800 gigatons is in the atmosphere. Have you plans on doing direct air capture or working with direct air capture companies, for example, to tackle that 800 gigatons?
So our technique removes some of the CO2 from the atmosphere, but our target at the moment is really to curb the amount of CO2 that we are releasing. For me, as an engineer, direct air capture is too early. It's not the way forward. I will give you an example of our plan for our first CO2 capture plant. We are going to treat 8 billion meter cube of air. But it's called flue gas. This flue gas contains 20% of CO2. And it's going to cost us about $40 per ton of CO2 to remove the CO2. If we do direct air capture and we treat 8 billion meter cube of air just to remove 400 ppm of CO2, that will cost us $1,500 per ton. That is my issue with direct air capture. I prefer to go after the concentrated source first than spending money for DAC, where we are adding more CO2 in the atmosphere than DAC could ever curb. So let's go with the concentrated source first. And then once we've cleaned that up, we will have a lot more knowledge on CO2 capture, we can go after dilute sources like direct air. But for me at the moment, I'm going for the concentrated source. But I'm not stopping anybody who wants to do DAC. It's fine for me. For me, the solution to climate change is there's no silver bullet, but there's silver buckshot. Anything that reduce the amount of CO2 in the atmosphere is good for me.
Nice. Cool. Arnaud, we're coming towards the end of the podcast now. Is there any question I haven't asked that you wish I had, or any aspect of this we haven't touched on that you think it's important for people to be aware of?
I would say about the Guardian's article about carbon offset and the impact that this could have on our project and other projects, because that's a sore subject for me, I have to admit.
Sure. Tell me about it.
Yeah, so the Guardian published some articles that proves that most of the carbon offset, I'm not going to call it scams, but they are not as efficient as they are reported to be. And it's, for me, it is not surprising at all, because when you see that people were buying carbon offset for $2 to $3 a ton, you know that this is not physically possible. It does not cost $2 to $3 to remove a ton of CO2. So you knew that there was something fishy around here. And there's some companies like Vera or Gold Standard that really need to have a look at what they are doing and need to be a lot more stringent on their process and to vet the CO2 capture processes properly, because it is going to hurt us at the end. Because if people don't trust carbon offset, there's no way somebody is going to give me $50 to remove a ton of CO2. So that is a very sore subject for me. That I'm glad the Guardian finally said something, because It is a failure of the market. It is a failure of politicians that force people to do something about climate change, about CO2, and there is a void. Nobody is able to provide with those carbon credit. So people will find a way. And this way was those very cheap carbon offset, which were not linked to anything, unfortunately.
Yeah. No, it's a valid point. Yeah, totally get it. Cool. Great. Arnaud, that's been really interesting. If people would like to know more about yourself or any of the things we discussed in the podcast today, where would you have me direct them?
Well, they can contact me on LinkedIn. I'm more than happy to answer any questions. We have a website that is being refurbished at the moment because we got some big announcement coming. So they can go to our website, which is decahydron.com. And as I said, send me an email, contact me on LinkedIn. I'm happy to answer any questions.
Cool. That's great, Arnaud. Thanks a million for coming on the podcast today.
Thank you for having me, Tom, and have a good day.